these are some things that we will need. We will need matrix algebra, knowledge of what a Fourier series is. But we will have to know how to solve second-order differential equations. Second-order linear differential equations have a general form: P, second derivative of y with respect to x, Q, first derivative with respect of y with respect to x, and R in x equals a function g, where P, Q, and R and G are continuous functions. Equations of this type arise in the study of motion of a spring. Let's look at the case where G equals 0. This gives the equation P, second derivative of y with respect to x, Q, first derivative of y with respect to x, and Ry equals 0. Two basic facts enable us to solve homogeneous linear equations. First of these says that if we know two solutions, y1 and y2, of such an equation, then the linear combination y equal to c1 y1 plus c2 y2 is also a solution. Theorem: if y1x and y2x are both solutions of the linear homogeneous equations, yc1 plus c2y is also a solution. Here's the proof for that theorem. Since y1 and y2 are solutions, we have P, second derivative of y1, Q, first derivative of y1, R, y1 equal to 0, and P, second derivative of y2, Q, first derivative of y2, and R, y2 equal to 0. Therefore, using the basic rules for differentiation, we have P, y double prime, Q, y prime, R, y equal to P, C1, y1 plus C2, y2 double prime, Q, C1, y1 plus C2, y2 prime, plus R, C1, y1 plus C2, y2. P, C, y double prime 1 plus C2, y double prime 2 plus Q, C1, y1 prime plus C2, y2 prime plus R, C1, y1 plus C2, y2. All equal to C1 parentheses P double prime y, Q, y1 prime plus R, y plus C2 multiplied by P, y2 double prime, Q, y2 prime, R, y2. This all equals C1 at 0 and C2 at 0, which is equal to 0. Thus, y equal to C1, y1 plus C2, y2 is a solution. The other fact is that a theorem which says that the general solution of a linear combination of two linearly independent solutions y1 and y2. This means that neither y1 nor y2 is a constant multiple of the other. For instance, the functions x squared and 5x squared are linearly dependent, but e to the x and x e to the x are linearly independent.